So we'll talk about a motion which is circular, meaning that an object is moving in a circle, okay, in a circular path. So let's say there's a circle, and this is the center of the circle, and an object is moving like this in this circular path, maybe like this counterclockwise. And so the radius of the circle is r. So this type of motion will be considered as circular motion. We'll need circular motion for, let's say, understanding how a fan works. I mean, how a fan rotates, or how Earth rotates around the sun, or how the wheel of a cycle actually rotates and goes forward. All those things, how the roller coaster works. Okay. So circular motion is ubiquitous in our world. মানে হচ্ছে এটা সব জায়গায় দেখা যায়. So we'll basically develop the theory of circular motion, and we'll connect this with the real life examples. We'll see 4 or 5 examples today. But before that, if we want to actually tackle circular motion, then first question is, what type of coordinate system should we use? So whenever we are talking about the coordinate systems, we say that there are Cartesian and polar coordinate systems. And polar coordinate systems are especially useful when you're talking about motion in a circle, because in Cartesian coordinate system, you will have 2 variables to specify a point, and in polar coordinate system, you also have 2 variables to specify a point. But the plus point is this, that the radius is fixed. So if I talk about that, this is the x-axis and this is the y-axis. So this is x, this is y. So this is the I hat direction and this is the j hat direction. This is r, this is theta. In that case, the particle is here, and you say, well, the position is r comma theta, and in Cartesian coordinate, you will say that the position is, let's say, x comma y. But whenever the particle moves, and the particle might be here now, in that case, you'll say, well, now the position is x prime comma y prime, but in polar coordinate system, the position will be r comma theta prime. So whenever the particle moves, you will have a new position in both x coordinate and y coordinate. But in polar coordinate, the radius is basically fixed. So all you have to do is change your theta. So you'll have to deal with a less number of variables or less number of values in polar coordinate. That's why we'll always use the polar coordinate to tackle the circular motion. Is it clear? We talked about this in
Sir, can you
coordinate
repeat that
systems.
again?
Yeah, so we said that we talked about this in the coordinate system introduction also, that whenever the particle is moving in a circle, then you will choose polar coordinate to actually describe the motion. Because in Cartesian coordinate, to describe every point, you need 2 coordinates. So to describe 2 points, you need 4 coordinates. But in polar coordinate, the r is fixed. It's not going to change, right? So all you have to care about is the theta. You know? So you need less number of variables. Like here, you need 3 variables or 3 values to specify two particular points. যেখানে Cartesian-এ তোমার 4টা variable লাগে, right? Because here you have just
Yes,
r,
sir.
theta, and theta prime. Yeah. Question? Right. So now we talked about the polar coordinate system before, but let's now think how to develop the unit vectors in polar coordinate system. So you know that the unit vector to x-axis, we define that to be I hat. The unit vector to y-axis, we define that to be j hat. Since in polar coordinate system we have 2 variables, r and theta, we also need unit vectors, like here. So we'll define them to be r hat and theta hat. Those will be unit vectors in our polar coordinate system. And what does those mean, or how do we see the direction of these polar coordinates? So if you draw a circle again, so I'm talking about this circle that I have already drawn. So this is the position vector R, this black one. We already have drawn this. Now, in which direction will this R increase? So let's say you have a bigger circle. Let's draw a bigger circle than this. So you have a bigger circle. Now, the position of a particle in the same direction will be maybe here. So this will be now the position of the particle in this bigger circle. So R is increasing in this direction, তাই না? এটা বুঝতে পারছো যে একটা পার্টিকুলার ডিরেকশনে আর হচ্ছে রেডিয়ালি আউটওয়ার্ড বাড়তে থাকে। রেডিয়ালি
Yes,
আউটওয়ার্ড
sir.
মানে হচ্ছে সেন্টার থেকে জাস্ট বাইরের দিকে বাড়ছে। সো আবার যদি এইখানের কথা চিন্তা করি, এটা ছিল হচ্ছে তোমার আর, তাই না? তাহলে এইখানে সেম ডিরেকশনে আরটা বাড়বে হচ্ছে এইদিকে, রাইট? সো এখন I hat এর ডিরেকশন অ্যাকচুয়ালি কোনটা? I hat is in the direction where x is increasing, right? Similarly, j hat is the direction where y is increasing. তাহলে r hat হবে সেই ডিরেকশনে যেদিকে r ইনক্রিজ করছে। So for example, this is the direction of r hat in this particular case. This is the direction of r hat in this particular case. So r hat, the unit vector r hat, it's not a constant. It depends on time or it depends on position. Generally, আমরা এতদিন পর্যন্ত যা unit vector দেখেছি I hat and j hat, they do not depend on position. They are always, I hat is always in this direction, in positive x-axis or in the direction where x is increasing like this. J hat is always in this direction. But r hat, that depends on your specific position or time. ঠিক আছে? তাহলে যেখানেই হোক, আমরা সার্কেলের যে কোনো জায়গায় হোক, আমরা যদি বলি যে r হ্যাটটা কোন দিকে হবে, r hat is in the direction of increasing r. যেদিকে r ইনক্রিজ করছে তার মানে r hat এর ডিরেকশনটা হচ্ছে it's radially outward, মানে সেন্টার থেকে জাস্ট রেডিয়াস বরাবর বাইরের দিকে হবে r hat. Okay. So where is the theta hat? In this case, we defined our positive theta to be anti-clockwise, right? Since it's anti-clockwise, so we'll so theta is increasing in anti-clockwise direction, but we need a specific direction, right? So let me just remove this. So I'll draw another circle here. So we said that this is basically your r, this is theta, and we're saying that this is the r hat direction here. Okay? We need the theta hat direction. So theta to increase counterclockwise. We'll choose at this point, we'll choose a tangent line to the circle to specify the direction of theta. So theta hat will be like this. Okay, so theta hat will be the tangent to this particular point. Okay, so if I write this direction, this will be the direction of theta hat. এখন দেখো, unit vector গুলো always perpendicular to each other. So r hat and theta hat, they are perpendicular to each other, obviously, because a radius vector always makes a 90-degree angle with the tangent vector. মানে কোন একটা সার্কেলে যদি তুমি একটা স্পর্শক রেখা নাও, তার সাথে রেডিয়াসটা অলওয়েজ হচ্ছে 90-degree angle ক্রিয়েট করে। So they have also 90-degree angles between them. তাহলে পার্টিকেলটা যখন এইখানে চলে আসবে, তখন তার রেডিয়াস ভেক্টরটা হবে এরকম। So this is the r in that case, and this will be the theta, maybe theta prime or something like that. Okay, so তখন r hatটা হবে হচ্ছে radially outward, আমরা যেরকম বলেছি, in this direction, and theta hat will be again tangent to this point. So theta hat will be in this direction. এটা কি ক্লিয়ার? r hat আর theta hat কোন দিকে হবে? theta hat is always tangent to the circle, আর যদি counterclockwise direction আমরা positive হিসেবে define করি, then it's tangent to the circle in the counterclockwise direction, and r hat is always radially outward. Do you have any question with this? Now the question is, how can you relate this theta hat and r hat with each other, with let's say with I hat and j hat? আমরা তো জেনারেলি I hat and j hat এ ক্যালকুলেশন করে অভ্যস্ত, সো আমাদের এদের মধ্যে একটা রিলেশন লাগবে. How do we do that? Now if you look closely, then these graphs look like this. So this was I hat and j hat, and this is basically r hat. This was the theta hat. And this angle is theta. You can clearly see that the angle between this line and this x-axis is theta. This angle is theta, and similarly this angle is also theta. So now, is this graph familiar to you? Is this familiar to anyone? So you have two angles. The r hat is theta angle. It creates theta angle with the I hat direction, x direction, and the theta hat creates theta angle with the j hat direction. Anyone, can you tell me where did you see this particular
rotation of
problem?
the
The
transformation.
rotation of the coordinates. Yeah, exactly. So we can direct r hat is basically cos theta I hat plus sin theta j hat. There's an assignment also from this particular part. ওইখানে r hatটাকে বুঝলাম আমরা j I hat prime আর theta hatটাকে বুঝলাম j hat prime. We just write it like this. Minus sin theta I hat plus sin theta. So we can also write that r hat is a function of time, theta hat is a function of time, because you see they depend on the angle. So particle টা কোন একটা টাইমে হয়তো এখানে আছে, বাট এর পরের টাইমে সে আবার হচ্ছে এইখানে চলে গেছে. So it particularly depends on time যে r hat আর theta hat এর ভ্যালুটা কি হবে. It depends on theta, and theta actually depends on time. Okay? So এক এক টাইমে তার পজিশন এক এক রকম, তার থিটা এক এক রকম. So you can say that this r hat and theta hat are related like this. এটা নিয়ে কারো কোনো প্রবলেম আছে? Anyone?
No, sir.
So now how do we define the position in this polar coordinate system? The position of a particle. Now the position of a particle is always denoted by r. Let's say r is a function of time. So that will be given by let's say its position from the center is always r. Whatever this is, it is at a distance of r from the center, and will denote the direction by r vector. Okay? So that's how we denote the position. Its distance from the origin is always r, and the direction is r hat. So it precisely describes the position of the particle, because you see that আমি যদি বলি যে এটা r hat-এর ডিরেকশন কোনটা, তাহলে তুমি সাথে সাথে বুঝে যাও পার্টিকেলটা কোথায় আছে. আমি যদি বলি r hat-এর ডিরেকশন হচ্ছে এইটা, এটা হচ্ছে r hat, তাহলে তুমি সাথে সাথে বুঝে যাবে যে সেন্টার থেকে পার্টিকেলটা হচ্ছে এতটুকু দূরে, এক্স্যাক্টলি এখানে আছে. So this precisely describes the position of the particle. আর যদি আরো ডিটেইলে জানতে চাও, then r of t, that will be basically equal to xi hat plus yj hat. আর x তো তুমি জানো যে তোমার যদি r থাকে কোনো একটা, so if you have something like this is x, this is y, and this is maybe this is r, and it makes an angle theta, then you know that the x component is basically r cos theta, right? And y component is basically r sin theta. Then, so in that case, if you take the r common, then this will be cosine theta I hat plus sin theta j hat. So this is basically r, and you know that cosine theta I hat plus sin theta j hat, that's nothing but r hat. So from here, you can also see that the position is given by r into r hat. So you can either find this from intuition, or you can also find this from calculation. So that's the position of a particle in polar coordinate system. Rather than x I hat plus y j hat, we'll just write it as r and r hat of t. Is there a question? So let's talk about the velocity of a particle. Velocity of a particle, we already know from kinematics that velocity of a particle is basically given by the differentiation of the particle with respect to time. We can also talk about the average velocity. Average velocity will be given by position at some time t plus delta t minus position at some time t divided by delta t. So you can find that. Let's say the particle in terms of circular motion, it might look like this. So you have this circle, and maybe at some time t, the particle was here. At some time t, the particle was here. So it's a, this is the position r hat at time t, and after some time the particle might have moved here. This is the position of the particle, and at that time also this is the position r hat of t plus delta t, something like that. So আমরা এইখান থেকে actually displacement বের করতে পারবো. I'm not going there. I'll just tell you how to calculate the regular velocity. You can also find the average velocity from here, okay? Because our position at t plus delta t is nothing but r into r hat of t plus delta t. Similarly, position at time t is nothing but r into r hat of t. You can plug these two things in this equation, and you'll find how to calculate the average velocity. But let's move on to finding the instantaneous velocity, which is more important for us to calculate. Now, it's basically telling you to differentiate the r vector, which is nothing but r into r hat. Now, r, the radius of the circle, that's the constant. We do not have to worry about that. So we'll just take that outside, and we'll just differentiate r hat. And r hat is given by cosine theta I hat plus sin theta j hat. So we'll write it cosine theta I hat plus sin theta j hat, right? Now, if you differentiate cosine theta, what do you get?
Minus sin theta.
Is this all? Is there
I.
something else? I, obviously, but there is something else. So look, you are differentiating with respect to time, and you're differentiating actually theta, right? So the chain rule should
There
apply.
is no differentiation. It should be
Yes.
0.
No, it should be d theta dt. Theta is dependent on time, remember?
Ah,
So theta যদি টাইমের উপর ডিপেন্ড না করতো তাহলে এটা 0 হয়ে যেত d theta dt টা। But theta তো টাইমের উপর ডিপেন্ড করে, সো সাথে একটা d theta dt আনতে হবে। That's the chain rule, right? বুঝতে পেরেছো এটা?
yes, sir.
And if you differentiate sin theta, you get cosine theta. Similarly, you write a d theta dt with that, and you have j hat. So if you take this d theta dt common, then d theta dt here minus sin theta I hat plus Sine of theta j hat. Can you tell me what is minus sine theta I hat plus cosine theta j hat? Have you seen this before?
Theta t vector.
Yeah. It's basically the theta hat unit vector, right? So we can just write directly that this is r d theta dt, and this is theta hat. We are saying that the velocity at any time is given by r, some number d theta dt, and the direction is theta hat. Now, so far, what we have done is pure mathematical calculations. There was no physical intuition between that, but now we'll see the physics. So d theta dt, theta is the angular position, right? So how can you define the differentiation of a position? যে কোনো পজিশনকে তুমি যদি ডিফারেন্সিয়েট করো তাহলে তুমি কি পাও অ্যাকচুয়ালি? What do you get if you differentiate something? Differentiate some position. What do you get?
So velocity, sir.
You get velocity. Since you are differentiating angular position, you'll get something called angular velocity. And let's define that to some number called omega. This is not W, this is called omega. Okay. So we are defining that omega, angular velocity, is equal to d theta dt. That's the number. Yeah? That's one kind of velocity. And it has a unit of radian per second. Since angle is defined in terms of radian and time is defined in terms of seconds, so the unit is radian per second. So you can also write your velocity, the linear velocity, as r omega, and the direction is theta hat. So in terms of magnitude, v equals to omega r. And in terms of my vector, it's omega r, and the direction is theta hat. But what does this direction theta hat mean to you? This theta hat direction means that whenever a particle is, let's say, here, and it's moving in this circle, then the direction of the velocity will be in the direction of theta hat. And what was the direction of theta hat? It was always tangent to the trajectory. So the particle will have a velocity in this direction. So when the particle is here, the particle will have a velocity in this direction. If the particle moves in the circle and it's here now, this green point now, the velocity of the particle will be again in the direction of theta hat, and it will be tangent to the circle. Similarly, if the particle moves here, then the velocity of the particle will be now in this direction. Now you see that the pure mathematical calculations that we have done actually gives you something physical. So it tells you that whenever you are rotating something in a circle, then the velocity, instantaneous velocity of that thing is always tangent to the circle. So মনে করো তুমি একটা পার্টিকেলকে এইভাবে সার্কুলার পাথে রোটেট করাচ্ছো, so like in this counterclockwise fashion, and you let that particle go at exactly this position. মানে পার্টিকেলটা যখনই এইখানে চলে আসলো, তখন তুমি পার্টিকেলটাকে ছেড়ে দিলা. Where will this particle go? What do you think?
So এটা round ঘুরতে থাকবে।
No, you're letting that particle go. If you let that particle go, then it will not move in a
একদম
circle, right?
এই সার্কেল বরাবর বের হয়ে যাবে, এই পার্টিকেল হচ্ছে এই সোজা বরাবর বের হয়ে যাবে তাহলে।
Because at this point it had an instantaneous velocity in this direction, right? So যখনই আমি এইখানে এনে ছেড়ে দেব, পার্টিকেলটা হচ্ছে সোজা বরাবর চলে যাবে, রাউন্ড করে পড়বে, এটা জাস্ট সোজা চলে যাবে। সিমিলারলি আমি যদি এই গ্রিন পজিশনে ছেড়ে দিই পার্টিকেলটাকে ঘোরাতে ঘোরাতে, তাহলে পার্টিকেলটা হচ্ছে সোজা উপরে উঠে যাবে। এটা বুঝতে পেরেছো সবাই?
জি স্যার।
So you'll see this example in your life in many cases. The velocity is always tangent to the circle. So যখনই তুমি ছেড়ে দিবে, যে position ছেড়ে দিবে, you would like to move like this. For example, whenever you take a turn, so let's say you're riding a bike or something like that. There is a turn in the road like this. এরকম যদি কোনো একটা টার্ন থাকে তখন তুমি যখন মুভ করো ইউ অ্যাকচুয়ালি তুমি এখান দিয়ে আসছিল এখানে ছিল তুমি টার্নে না যেয়ে ইউ টেন্ড টু মুভ ট্যানজেন্ট টু দ্য ট্রাজেক্টরি, তোমার এইদিকে মুভ করার তোমার প্রবণতা থাকে। But you actually make a turn by using the wheel and like this. So you actually move like this ultimately. Right? But you actually make that turn by using the wheel and you actually bend sometime. Right? So এইসব কিছু করে তুমি actually করো, but your natural tendency is to go tangent to the trajectory. So যখন একটা গাড়ি let's say তুমি সিএনজিতে বসে আছো, যখন এটা একটা শার্প টার্ন নেয় তখন তোমার মনে হয় যে তুমি বাইরের দিকে চলে যাচ্ছ, রাইট? হ্যাভ ইউ ফেল দ্যাট? যে মনে হয় যে তুমি let's say sideways চলে যাচ্ছ, right? That's not actually sideways, that's actually tangent to that curve of the road. যে তুমি মনে হয় যে তুমি ছিটকে যাচ্ছ, এটা কেউ ফিল করেছো? লাইক রিক্সাও এটা ফিল করে কথা যখন এটা হচ্ছে এক সাইডে তোমার চলে যাও তুমি, রাইট? দ্যাটস
Yes,
যখন
sir.
বামে টার্ন নিচ্ছে তখন তুমি ডান দিকে চলে যাচ্ছ, যখন ডানে টার্ন নিচ্ছে তখন তুমি বাম দিকে চলে যাও। এটা আসলে বাম দিকে যাওয়ার প্রবণতা, এটা হচ্ছে এই ট্যানজেন্ট বরাবর চলে যাওয়ার প্রবণতাটা। বিকজ whenever you are trying to turn, your inertia lets you move in the tangent direction. বাট তখন হচ্ছে ওইটা তুমি ব্রেক করিয়ে তারপর হচ্ছে একটু হেলে গিয়ে তুমি হচ্ছে তারপর সার্কুলার Is it clear?
Yes, sir.
Okay, so we talked about this motion. So now let's talk about the acceleration in circular motion. So we talked about the position and velocity of the particle. Now the thing that is left is the acceleration of the particle. So now, how do we calculate the acceleration of this particle? Again, acceleration is nothing but dv dt from our kinematics. Also, if you want to find the average acceleration, then it's simply v at some time t plus delta t minus v at some time t divided by delta t. So it's basically vf minus vl divided by delta t. We're not going to talk much about that. We'll see a problem to calculate that average acceleration. But let's now focus on the average, the normal acceleration, the instantaneous acceleration. So we have found that the velocity is r omega theta hat of t. We're going to just use that here. So our acceleration is d dt of r omega theta hat. Now here, your r is a constant, obviously, so you can take that outside and you differentiate just omega and theta hat of t. Now you have two quantities that both can depend on time. Omega can depend on time, theta hat can also depend on time. Omega হচ্ছে angular velocity, এটা টাইমের উপর obviously depend করে। Because for example, যখন তুমি ফ্যানের সুইচটা অন করো তখন ফ্যানের স্পিড আস্তে আস্তে বাড়তে থাকে, রাইট? রোটেশনাল স্পিডটা আস্তে আস্তে বাড়তে থাকে। So omega is changing with time. So that's one example where omega is changing. Or whenever you speed up your cycle or bike or let's say car, then it starts from zero angular velocity and it starts rotating faster and faster. So omega can depend on time. Theta hat also depends on time. তাহলে আমার দুইটা কোয়ান্টিটি আছে যারা মাল্টিপ্লাইড আকারে আছে যাদেরকে ডিফারেন্সিয়েট করতে হবে। What should we do? Which rule should we use to differentiate two variables? Anyone? It's the easy rule, right? So if you have two quantities multiplied and you have to differentiate that, then you first take u outside and you differentiate v, then you take v outside and then you differentiate u. Okay, so that's how you actually do this. Right? So for example, in this particular case, you have r and it's omega into theta hat of t. So first of all, you can take this omega outside and you can differentiate just theta hat, and then you can take theta hat outside and you can just differentiate omega. That will be the differentiation of this function. Okay. Now we'll do this here. I'll write the last equation to the left part. So first of all, you have to differentiate theta hat. And you know that theta hat is nothing but minus sine theta I hat plus cosine theta j hat. Okay. Now, how do you differentiate that? So first of all, if you differentiate sine theta, you are going to get cosine of theta, and you have to write a d theta dt with that I hat. Then if you differentiate cosine theta, you'll get minus sine theta, and you'll write a d theta dt with that for the chain rule j hat. If you take minus d theta dt common, then you get cosine theta I hat plus sine theta j. Is this familiar to you? The cosine theta I hat plus sine theta j, is it familiar to you? We go back, you can see
R.
that that's exactly r hat. Right? Cosine theta I hat plus sine theta j. So this is basically minus omega into r. We define d theta dt to be omega. So the differentiation of this quantity d dt of theta hat gives you minus omega r hat. And d omega dt in the second term, there is d omega dt. Since omega is the angular velocity, d omega dt must be the angular acceleration. And velocity ke আমরা differentiate করছি. So that's an acceleration. And it's the differentiation of angular velocity. It's angular acceleration, and we define that with alpha. Alpha is equal to d omega. So that means that this is r into omega into minus omega r hat plus theta hat of t into alpha. So finally, our acceleration is basically minus omega square r hat plus alpha r theta hat. I'm just not writing theta hat as a function of time and r hat as a function of time to save the complications. So this is the final form of our acceleration. And you see how this thing actually came from. After all these calculations, we find that acceleration is minus omega square r hat plus alpha r theta hat. And this acceleration has two components. One is the r hat component and another is the theta hat component. And we'll talk about both of them. This component and this component. The first component, can you tell me what is the direction of this component? I mean, its magnitude is omega square r. What is the direction of this component? Which just by looking at the equation that it's omega square r hat, can you tell me the direction of this component? No one? So the hats always defines the direction, right? So in this particular case, the r hat is defining the direction, but it's not just r hat, it's minus r hat. So if your unit vector is out of the circle, if this is r hat, what should be the direction of minus r hat?
So inside the
The
circle.
opposite direction.
Inside of the circle. This is the direction of minus r hat. Similarly, If your, let's say, if your position is here, and you said this is the direction of your r hat, then the minus r hat will be in this direction. If your position is here, then this is the direction of r hat in that position. So this is the direction of r hat in that position. So the inward position is minus r hat, right? So everywhere in the circle, the direction of this acceleration component is towards the center of the circle. Do you see that? That wherever your particle is, the acceleration is always towards the center of the circle. And that's why we call this a centripetal acceleration. কেন্দ্রমুখী ত্বরণ. We call this centripetal acceleration. We denote this by AC. Okay. It's given by minus omega square r. The magnitude of centripetal acceleration is omega square r. You can also write this as, so you remember that omega v equals to omega r. So you can write omega equals to v divided by r. এটা কিন্তু এইভাবে লিখতে পারো v by r whole square into r. So এটা হবে হচ্ছে v square by r square into r. So এটাকে তুমি v square by r ও লিখতে পারো. So the centripetal acceleration, the first component of the acceleration, it is given by either omega square r, and the direction is always minus r hat, or v square by r, the direction is minus r hat. Centripetal acceleration magnitude হচ্ছে omega square r বা v square by r, আর direction হচ্ছে minus r hat, which means it is always towards the center of the circle. Since it's always towards the center of the circle, it's a center seeking acceleration. We'll call that centripetal acceleration. That's what this C means, centripetal. Is it clear to everyone? Why do we call this component centripetal? And the
Yes,
second
sir.
component, the second component has a direction of theta hat here. So since the second component has a direction of theta hat, it's always tangent to the circle. So if we now talk about a circle and a particle moving in a circle, then if the particle is here, then the tangent, then that second component of acceleration is always tangent to this trajectory. And it looks like this. So this is the direction of the tangential acceleration, and we'll call that AT. Since it's always tangent to the circle, the second one, we'll call that the tangential acceleration. So the tangential acceleration, and it will be denoted by AT, and simply alpha r, and the direction is theta hat. Both of these are proper accelerations, so that they have a unit of meter per second. You know that alpha should have a unit of radian per second square. If you look at this, okay. And so we can write the total acceleration. The total acceleration anytime can be written just as centripetal acceleration plus the tangential acceleration. Okay. Where the centripetal acceleration is minus omega square r hat, and the tangential acceleration is alpha r theta hat. So those acceleration are in those two directions. So at any time, you can have two type of acceleration. One is tangent to the trajectory, and another one is towards the center of the circle. Okay. So the total acceleration will be a linear sum of them. So total acceleration to AP, but we don't care about that. All we know is there is one acceleration which is towards the center of the circle, and there is another acceleration which is tangent to the trajectory. Is there any question up to this part?
No, sir.
Everyone okay with this?
Yes, sir.
Fine. Um, and we are going to talk about something called uniform circular motion. So as the name suggests, this is called uniform circular motion. So by uniform, we mean that the omega, the angular velocity, is a constant. Since it's uniform, the object moves in the circle uniformly. There is no change in the velocity, angular velocity of the object. For example, if you switch on your fan for the first few seconds, it will move, its angular velocity will start to increase, and after some time, it reaches its maximum angular speed or maximum angular velocity. After that, it moves with roughly a constant angular velocity, right? Its angular velocity doesn't decrease, its angular velocity doesn't increase, it moves with a constant angular velocity. And we'll call that motion a uniform circular motion. So that's one example. Or if you consider the orbit of Earth as a circle, then Earth roughly moves in a uniform circular motion around Sun. Or you can rotate any object with the same angular velocity, that will be a uniform circular motion. So uniform circular motion is also very ubiquitous in nature. So you can see uniform circular motion every now and then. Now, if omega is a constant, then what will be the value of alpha here? The angular acceleration. It was d omega dt. If omega is a constant, what will be the angular acceleration now? Yeah, tell me. You know this. If you differentiate a constant function, what do you get?
Zero.
It's zero, right? If you want to participate, you can also answer in the chat box, okay? So just do not say nothing. So the angular acceleration alpha becomes zero. If the angular acceleration becomes zero, then the only acceleration that survives is the centripetal acceleration, because the tangential acceleration becomes zero. Since tangential acceleration is alpha r theta hat, so that also becomes zero. So the only acceleration that survives is centripetal acceleration. That's omega square r hat. So in any case, there will be some centripetal acceleration, whether it's uniform circular motion or non-uniform circular motion, it doesn't matter. Centripetal acceleration is always there. আর tangential acceleration থাকবে কিনা সেটা depend করে circular motion টা কি uniform নাকি non-uniform. যদি uniform হয়, then there is no tangential acceleration, and if it's not uniform, then there is some tangential acceleration. But centripetal acceleration is a must. If you want to have a circular motion, you must have a centripetal acceleration. Without centripetal acceleration, there is no circular motion. So since you have a centripetal acceleration, yeah.
The tangent acceleration, what does it depend on?
Tangential acceleration. It depends on the angular acceleration alpha. So if your particle is not speeding up or speeding down, মানে এটা rotational speed যদি change না হয়, তাহলে এটা কোনো tangential acceleration নেই. For example, the example of fan, when it reaches its full speed, then it's moving with a constant angular velocity. There is no tangential acceleration, there is only centripetal acceleration.
Okay, sir. Thank you, sir.
For example, the Earth is moving around the sun, and if we assume the period, the orbit of Earth to be a circular orbit, then there is no tangential motion to that. There is only centripetal acceleration, no tangential acceleration. So only the centripetal acceleration survives in uniform circular motion, which you can find either by writing omega square r or by writing v square by r. So তুমি যদি radius জানো একটা circular আর যদি তার linear velocity জানো or angular velocity জানো, you can calculate the centripetal accelerations. And if there is some acceleration, there must be some force. কোনো না কোনো force তো acceleration এর provide করবে, right? So we call that force the centripetal force. যে ফোর্সের কারণে এই centripetal acceleration create হয়, we call that the centripetal force, which is obviously mass into centripetal acceleration. So you can also write centripetal force as m omega square I or mv square divided by r. So this is the force which is responsible for centripetal acceleration or for circular motion. So তোমার যদি কোনো circular motion যদি তুমি পেতে চাও, in any case, if you just want a circular motion, there must be some centripetal force. তাহলে এমন একটা ফোর্স থাকতে হবে যেটা অলওয়েজ হচ্ছে সেন্টারের দিকে। Otherwise তুমি কখনো circular motion পাবে না। So now there is an idea of centripetal force বা কেন্দ্রমুখী বল. Have anyone heard of something called centrifugal force বা কেন্দ্রবিমুখী বল?
Yes, sir.
Do you think it is necessary to keep an object in the circle? Let's say a particle is here at this position. So the centripetal force is obviously towards the center of the circle. This is the direction of centripetal force. And do you need an opposite force in this direction, the centrifugal force? Let's call that Fc prime, to keep this object in the circular path. Anyone? Do you think so? মানে সেন্ট্রিফিউগাল ফোর্সের আইডিয়াটা কিভাবে আসছে, যে এটা হচ্ছে সেন্টার থেকে বাইরের দিকে, ইজ ইট? Is it the idea of centrifugal force? সেন্ট্রিপেটাল ফোর্সটা তো ভিতর দিকে, সেন্ট্রিফিউগাল ফোর্সটা কি বাইরের দিকে?
No, sir. It's towards the tangent.
No, centripetal force is not towards tangent. It's actually outward from the circle. But the thing is that this force doesn't exist. In our whole calculation, you see, there was no force which is outward to the circle. So the centrifugal force, it's not a real force. It's a fictitious force. Fictitious force মানে হচ্ছে it's a unreal force, so it's an imaginary force, or it's also called pseudo force. It's not actually there. Centrifugal force হলো কিছু actually এখানে নেই, কিন্তু কিছু ক্যালকুলেশনে এই ইমাজিনারি ফোর্সটা ধরে নিলে ক্যালকুলেশনটা ঠিকঠাক করা যায়। যেমন নিউটন সেকেন্ড ল অনলি হোল্ড করে হচ্ছে ইনার্শিয়াল রেফারেন্স ফ্রেমে, ওইটা নন ইনার্শিয়াল রেফারেন্স ফ্রেমে হোল্ড করে না। নন ইনার্শিয়াল রেফারেন্স ফ্রেমে যখন এই সার্কুলার মোশনে ক্যালকুলেশন করতে হয়, তখন হচ্ছে এই সেন্ট্রিফিউগাল ফোর্সের আইডিয়াটা এনে তারপর করতে হয়। But we will not need that. We will calculate everything from inertial frame of reference. So centrifugal force বলে আমাদের কাছে কিছু নেই. There's only one force, and that is the centripetal force. Remember that. And if you want to see how this centripetal force actually makes an object move in a circle, then you can see that. So let's say an object was initially trying to move in this direction. But you have a force which is, let's say, perpendicular to this object. So this is the direction of force, or this is the direction of acceleration also. So তাহলে অবজেক্টটা কোন দিকে যাবে? Generally, if you have some v, if you want to some have some v, then that v equals to v naught plus at, right? That means the final velocity will be in the direction of v naught and acceleration into time. So তার মানে এটা v naught আর acceleration এর direction এ মাঝামাঝি কোথাও যাবে. So let's say the particle moves in this direction. তারপর পার্টিকেলটা এখানে আসলো. এখন পার্টিকেলটার ভেলোসিটি হচ্ছে এই দিকে. So now the particle has a velocity in this direction. এখনো তার সেন্টারের দিকে মানে তার সাথে পারপেন্ডিকুলার করে আরেকটা ফোর্স আছে বা অ্যাক্সেলারেশন আছে এদিকে. তখন পার্টিকেলটা কোন দিকে মুভ করতে চাইবে? So let me draw this. So let me show you the bigger picture. So then the particle moves like this in this direction, and the particle may have moved here. যেভাবে মুভ করতে হতো এখানে এসেছে. এখন পার্টিকেলটা মুভ করছে হচ্ছে এইদিকে. পার্টিকেলটা ইনিশিয়াল ভেলোসিটি হচ্ছে এইদিকে, আর তার উপর একটা পারপেন্ডিকুলারলি আরেকটা অ্যাক্সেলারেশন কাজ করছে. সো দেখো আমাদের সার্কুলার মোশনে অ্যাক্সেলারেশন আর ভেলোসিটি কিন্তু পারপেন্ডিকুলার. ভেলোসিটি ডিরেকশন হচ্ছে থিটা হ্যাট আর সেন্টিমিটার অ্যাক্সেলারেশনের ডিরেকশন হচ্ছে আর হ্যাট, রাইট? সো ইউনিফর্ম সার্কুলার মোশনে সেন্টিমিটার অ্যাক্সেলারেশন ইজ অলওয়েজ পারপেন্ডিকুলার টু দ্য ভেলোসিটি. সো এখন এই পার্টিকেলটা কোথায় যেতে চাইবে? এই পার্টিকেলটা এখন নিশ্চয়ই এইদিকে কোথাও যেতে চাইবে. সো পার্টিকেলটা মেবি এখন এইখানে আসবে, যার ভেলোসিটি হচ্ছে এইদিকে. এর উপর এখন আরেকটা পারপেন্ডিকুলার ফোর্স কাজ করছে মেবি এইরকম. সো পার্টিকেলটা এখন মেবি যেতে চাইবে হচ্ছে এই দিক বরাবর. সো পার্টিকেলটা এখন এইখানে আসবে. The particle has a velocity in this direction, but still a force perpendicular to this is acting. So now the particle would like to move in this direction. The particle will be here. So can you see where this is going? আবারও যদি এটার উপর if you have a perpendicular force or acceleration to that, the particle would like to move maybe in this direction. So the particle will be down here. So you see it is roughly making a circular motion. Okay. So if you have a force which is always perpendicular to the velocity, then there will be a circular motion. এটা বুঝতে পেরেছো?
Yes, sir.
This now defines some quantity of interest called the time period. So if you have a particle moving in a circle, and if it starts from here and then moves the whole circle, again reaches the same point, মানে হচ্ছে একটা পয়েন্ট যদি একটা whole circle complete করে আসে, the time needed for this is called the time period. Time period is defined as t. So it's the basically denotes the time needed to complete a whole circle. সার্কেলে পুরো সার্কেলটা একবার করে আসতে যে টাইম লাগে, that's the time period. It is denoted by t, capital T. And since you know that omega is delta theta by delta t, যদি পুরো সার্কেলটাকে একবার ঘুরে আসে তাহলে কতটুকু অ্যাঙ্গেল ট্রাভেল করবে বলো তো? It moves the whole
360
circle 360 degree, or in radian it's twice pi. And আমরা বলছি ওই টাইমটাকে আমরা ডিফাইন করছি হচ্ছে t হিসেবে. So that's the time t. So we say that t is basically equal to twice pi by omega. So you can write t, you can find t if you know the angular velocity. And since angular velocity, since you know another relation that v equals to omega r, so omega is equal to v by r. So you can also write from here that t equals to twice by r divided by v. Okay, so you can find the time period from these two equations, either from omega or from v and r. Okay. Any question in the time period curve? Okay, let's now move on to examples.
Sir, can you go backwards? I need to take the notes for a minute. Thank you, sir. I'm done, sir.
Let's see an example. So let's say you have a fan blade. So say you have a fan. So there's a blade of this fan that looks like this. So I'm just showing the blade in one dimension. So this is the blade of the fan, and that blade is moving, obviously moving in a circle. A fan blade moves in a circle, and the radius of that fan blade is, let's say, 1 meter. And we define 2 points. One point or one particle is at the edge of the fan blade, and another particle is at the middle of the fan blade. Okay? The blue and the green ones. So the question asks you to find, so let's say this fan is moving at a constant angular speed of velocity of 2 radian per second. So this question asks you to find the linear velocity or the tangential velocity let's call that A, let's call that B. So it asks you to find the tangential velocity of point A and point B. Now for point B, you know that V equals to omega R. So VV equals to omega RB, since they have the same angular velocity. So it's simply 2, and the radius of point B is 1 meter. So that's simply 2 meter per second, and that's very easy to calculate. But what about the tangential velocity of point A? Is it really moving in a circle of 1 meter, or is it moving in a different circle? So although the whole blade is moving in the circle, the tip of the blade, point B, is moving in a circle of radius R, but point A is moving in a circle like this. It's not moving in a radius in a circle R, rather it's moving in a circle so it's moving in a circle in this 0.5 meter radius. So যখনই তুমি হচ্ছে A পয়েন্টের angular linear velocity বা tangential velocity calculate করবে, you have to write it as radius of A, so that will be 2 into 0.5 meter per second. So that will be 1 meter per second. Is it clear to everyone that even if an object is rotating in a circle, different point in that object will have different tangential velocity, although they have the same angular velocity? Is it clear? Or is there any question? Okay. I think clear. Let's move on to example 2. So example 2 is a simple example that asks you to find the so let me show you the problem. This is I hat, this is J hat. And let's say a particle was at this green position, let's call that A, at some time and after some time it moves to position B. Okay, so you have to find what is the okay, let's say it's given that the angular velocity is 5 radian per second, and it asks you to find the average acceleration when it moves from A to B. So it tells you to find the average acceleration when the particle moves from A to B while it was rotating in this circle. Okay, and one thing is important here, that how do you calculate average acceleration? Average acceleration is nothing but final velocity. So here VB minus VA divided by the time it takes. Okay. That's the average velocity. Simple. So now, in which direction will the tangential velocity at point A be? A pointed tangential velocity টা কোন direction হবে? Yeah. You can just answer by telling me the direction.
A, sir, A.
বুঝছি। J hat or I hat or minus J hat or minus I hat. So you basically draw a tangent, right? That's the velocity of A. So it should be J hat. Now tell me, what will be the tangential velocity in the B position? In which direction?
Parallel to I hat
I hat or minus I hat?
Minus I had.
minus I hat.
That's the direction of VP minus I hat. So you can write VA as whatever the velocity it has and J hat, and you can write VB when whatever the speed is has and the direction is minus I hat. That's not tough to find the speed if you already know omega, because that's just omega r, right? So let's say it moves in a radius of path 2 meters. So that's just 5 into 2. So it's just 10 meter per second. So it's fine, it's easy. So this is basically 10 J hat, and this is basically minus 10 I hat. Okay? There's no problem with that. But you have to find the time also. What time does it take for going from A to B? How can you find that? Any idea? From all this information given, can you find the time that it will take for going from A to B?
From the first equation.
From the first equation, meaning the average acceleration?
Yes, sir.
No, you have to find the average acceleration. And for that, you have to find the time. See, you are going on a circular argument.
Sure, time
So-
period equation টা।
Yeah, you have to find the time period first. So the time period is twice pi by omega. So that's 2 pi by 5. And if you know the time period টা হচ্ছে একটা হোল সার্কেল করতে কতটুকু টাইম লাগে। তাহলে এখানে A থেকে B তে যেতে যে টাইম লাগছে সেটা ওই হোল সার্কেলের কয় ভাগের এক ভাগ? Yeah,
4 ভাগের এক।
1/4. So it's basically twice pi by 20. So it's basically pi by 10. That's the time that you will take to reach from A to B. And now finding average acceleration is very easy. So all you have to do is just plug in these numbers. So the average acceleration will simply become minus 10 I hat minus 10j hat divided by I by 10. So it's probably minus 100 I hat plus j hat divided by 5. That's just the average expression. So this example is just to illustrate you how to find the direction of tangential velocity if you are given the speed. Okay, the speed is same, it's a uniform circular motion. So the speed is not changing since omega is a constant. So, but how do you find the direction of velocity from there? Yeah, the position. Let's move on to a more realistic problem. So this problem is related to designing a roller coaster. So you know the roller coasters, we are talking about a circular roller coaster. So a roller coaster car will just move in this circle. So it will enter the circular path here, the car here. It will enter the circular path here, and it will move through this whole circular track. Maybe here it is the upside down version. So you're given the task to design this roller coaster. Okay. So why do people actually use roller coasters? Right? So they want to get the thrill. They want to experience the thrill. Let's say the speed, the feeling that he or she might fall down from the top position. That's the thrill that people look for in a roller coaster. So if you're given the job to design a roller coaster, how do you design that? কিভাবে মানুষকে তুমি maximum thrill দিতে পারতে? So basically, you'll design it like this. So I would design it like this, that there will be no roof in this roller coaster. Okay? So there is no roof to this roller coaster. So that at the top position, so let's say you are sitting in that roller coaster. Let me draw you. So this is you. You're sitting in that roller coaster. And maybe at the top position, this is you. Just the upside down version of you at the roller coaster. So you feel the thrill that at the top position, you feel the thrill of falling down. Because if there's a roof, then there's not much to worry about because you will be contained in that roller coaster. But if there's no roof, then you can get the thrill of falling down. That's the first thing that I'm going to do. The second thing I'm going to do is obviously there will be seat belts, but I can also remove that seat belts. So let's say no seat belt. It's not obviously recommended. Whenever you design a roller coaster, you'll make sure that there are seat belts. But let's, for the sake of our example, you see there is no seat belt. So you are trying to design a roller coaster that is very risky, but at the same time, which is very entertaining or very thrilling. Okay? So if there's no seat belt, then at the top point, if your roller coaster is moving very slowly, then you will just fall from the roller coaster at the top point. Is it clear that you'll just fall from the roller coaster at the top point if it's moving very slowly? Think about this, that there's no seatbelt, no roof, you're just moving slowly. So at the top point, you'll just fall downward. But if your roller coaster can move very fast, then you'll not fall even at the top point. Without any seatbelt, without any roof, you'll not fall. And our job is to find the minimum omega so that the person do not fall at the top position. Is it clear what is our objective? We want to find the minimum angular velocity
Yes, sir.
so the person do not fall at the top position. For that, we'll draw the force diagrams. So at point A, there are two forces. One is obviously the gravitational force mg, and another one is the normal force Fn. At point B, we have the gravitational force downward. But can you tell me at point B, where will be the normal force directing? Is it downward or upward?
Upwards, sir, still.
No.
Downward.
It will be downward because now you will be pushing the roller coaster surface in the upward direction by your feet. So the roller coaster will give you a force downward. Does it make sense?
Yes, sir, it does.
Okay. And now the centripetal acceleration, since it's moving in a circle, the centripetal acceleration is always towards the center of the circle, right? So when the person is at A, the centripetal acceleration will be in this direction, this red direction. So does the centripetal force. When the particle is at B, or the person is at B, the centripetal acceleration will be downwards, since it's the direction towards the center of the circle. Is that clear? Since the centripetal force is always towards the center of the circle, at point A, it is directing towards the center of the circle up. At point B, it is directing towards the center of the circle down. Any question? So at point A, all the forces will give rise to the centripetal force. So sum over all the forces will be mass into centripetal acceleration. So we'll write Fn j hat minus Fg j hat. That will be mass into acceleration. Acceleration is omega square r, and the direction is also j hat. So the normal direction force will be mg plus m omega square r. Okay, that's the result that you find from here. So the normal reaction force is greater than mg at the bottom point. But when the object is at the top point, then Fn is downward. So I'll write, so the same equation. Again, sum over all the forces must give rise to the centripetal force, MSC. So again, we have the normal reaction force Fn, but now Fn is downward. So I'll write it as minus j hat. Fg is also downward, minus j hat. Mass into acceleration omega square r, that's also downward. So again, minus j hat. Is it clear? Or is there any question? Okay. So Fn will be Fg minus m omega square r. So Fn will be, sorry, it should be minus Fg plus m omega square. So Fn will be m omega square r minus mg. Okay. That's the direction of the normal reaction force. That's the magnitude of normal reaction force at the top position. Now, whenever you are, let's say you're just going to fall from the top position. So you're at the top position and you're just going to fall. So you leave the contact with the roller coaster. And if you lose the contact with the roller coaster, what will happen to your normal reaction force? তুমি যদি জাস্ট কন্ট্যাক্টটা লুজ করে ফেলো রোলার কোস্টারের সাথে, তো নর্মাল রিঅ্যাকশন ফোর্স কত হয়ে যাবে? Normal reaction force is a contact force, right? If you are not in contact with the surface, if you are jumping, the normal reaction force is 0, right? So setting 0 there, you get m omega square r minus mg. So you'll get omega equal to root over g by r. Okay, and let's call that the critical omega. So এই ওমেগাতে যদি তুমি তোমার রোলার কোস্টারকে অপারেট করতে পারো তাহলে তুমি পড়ে যাবা, তো নর্মাল ফোর্স 0 হয়ে যাবে। বাট if your roller coaster is operated with a greater angular speed than this minimum speed, then you will not fall even at the top position. আইডিয়াটা বুঝতে পেরেছো সবাই?
Can you explain it again
Which part?
at the extent of falling if n equal to 0 from here?
Yes, whenever you are losing contact with the ground, isn't your normal force 0? Like say you are jumping from the ground, for example. You are now at the ground and the ground will give you some normal force because you are pushing against the ground. But whenever you are jumping and you just leave the ground, okay, now you have no longer any touch with the ground, then the normal force won't be 0 because there is no force that you are exerting on the ground. So the ground cannot exert any force on you because there is no contact. Is it okay?
Yeah, I got it.
So if your angular velocity is greater than this minimum angular velocity, then you'll not fall even at the top position. And this is the same case as a water bucket problem. So for a water bucket, you can actually try this at home. You cannot design a roller coaster at your home, but you can for sure design a water bucket. So let's say you have a bottle of water. So you have a
Sir.
bottle of water.
যদি ওখানে fn equals to 0 না হয় তাহলে কি হতো?
F n equal to 0 না হলে তুমি পড়বে না,
Oh,
simply. যেমন এখানেও তুমি পড়ছো না অ্যাকচুয়ালি, মানে যদি তুমি ওমেগার চেয়ে বড় ওমেগা সি এর চেয়ে বড় অ্যাঙ্গুলার ভেলোসিটিতে রোটেট করো তাহলে
sir.
এফএন আর 0 হবে না, এফএন টা পজিটিভ কিছু একটা হবে। So that means you are staying with that roller coaster. You are not losing contact with that roller coaster. বুঝতে পেরেছো?
জি স্যার, থ্যাংক ইউ।
So same problem is the water bucket problem. Let's say you are rotating a water bucket or a bottle of water with your hand, and if you can rotate this water bucket greater than g by r angular velocity, then the water in that bucket or in that bottle will not fall even from the top position. Okay, এটা ট্রাই করতে পারো। খুবই আস্তে আস্তে যদি ঘোরাও দেখবা যে একদম যখন টপ পজিশনে চলে আসছে তখন ওই বাকেট বা বটল থেকে the water is dropping from there. But if you can rotate faster, the water will not fall. That's the same problem as water. I'll just give you one more example. If your name is like the name in the attendance sheet, you do not have to write your ID. If your name has ID in it, you do not have to write your ID. But if your name is something else, then you can write your ID in the chat box for the attendance. Let's say you're rotating something in a circle by using a string. মানে একটা সুতায় কিছু একটা বেঁধে তারপর তুমি হচ্ছে তাকে রোটেট করাচ্ছো, something like that. Like this, huh? So this is a string, this is a rope, and you're trying to rotate an object of mass m in this circular path by using that rope. This is your hand. So in that case, there must be some centripetal force, right, in this direction. Other than that, there will be no acceleration. Can anyone guess which force can give rise to this centripetal acceleration? So তুমি হাত দিয়ে একটা সুতার মধ্যে কিছু একটাকে বেঁধে তারপর হচ্ছে চারপাশে ঘোরাচ্ছো সার্কেলে। সো কোন ফোর্সটা অ্যাকচুয়ালি সেন্ট্রিপিটাল অ্যাক্সিলারেশন প্রোভাইড করতে পারে এখানে?
Tangential force.
টেনজেনশিয়াল ফোর্স তো না, ফোর্সটা হতে হবে সেন্টার বরাবর।
Force.
এগেইন ক্যান ইউ রিপিট?
রোপের ফোর্সটা
রোপের ফোর্স, the tension
Tension.
force.
জি।
Yeah, the tension force will give rise to centripetal force. So in this example, your tension force will be equal to the centripetal force, meaning the mass into acceleration. So your tension will be m omega square r. So আমি যদি তোমাকে r দিয়ে দেই, let's say আমি বলে দিলাম যে পার্টিকেলটা ঘুরেছে তার মাস হচ্ছে 2 কেজি, your omega is 2 radian per second, and the radius is 0.2 meter. And you can exactly find what will be the tension in the rope. So the tension in the rope can be found from this centripetal force idea. It's the other way around. Generally, we find the acceleration from the force. Now here you can find the force from the acceleration from the circular motion. Okay? So কোনো জায়গায় টেনশনটা হচ্ছে সেন্টিপিটাল ফোর্স হিসেবে কাজ করবে, কোনো জায়গায় হচ্ছে ফ্রিকশন হচ্ছে সেন্টিপিটাল ফোর্স হিসেবে কাজ করবে, কোথাও হয়তো তোমার যে নর্মাল ফোর্স, যেমন এই এক্সাম্পলে নর্মাল ডিরেকশন ফোর্স আর গ্র্যাভিটেশনাল ফোর্স মিলে সেন্টিপিটাল ফোর্স হিসেবে কাজ করবে। Okay, I'm done for today. If you have any question, you can ask me. Otherwise, you can leave. I'll take the attendance from the participant list.